How's that? So I just want to pose a couple of problems on k-tuple regular graphs, because in Pascal's very nice talk, he mentioned this class of k-tuple regular graphs. And it's something I haven't thought about for a long time, but at the time I had a couple of open problems that I couldn't solve. And I don't think they've been solved since. So let me just pose them now, and they might still be interesting to people. So a graph is t-tuple regular, as Pascal said in his talk. Oh, sorry, that should say if t is a positive integer. I changed my notation, forgot to change k to t. That's t. If you have any two subsets of the vertex set with the same number of vertices less than or equal to t, if the induced subgraphs on x and y are isomorphic, then the number of common neighbors of the vertices in x is equal to the number of common neighbors of the vertices in y. So what does that mean? One tuple regular just simply means any two vertices have the same number of neighbors, so the graph is regular. Two tuple regular means not only any two vertices, but any two edges or any two non-edges have the same number of common neighbors, so that's the same as strongly regular. Now, at the other end, five tuple regular or higher, as Pascal mentioned this theorem, the only graphs that have this property are the disjoint union of n of a number of complete graphs all of the same size, or the complement of that, which is a regular complete multipartite graph, or the 5 cycle, or the 9 vertex graph, which is the line graph of K33, sometimes called L2 of 3. And what's more, 4 tuple regular graphs, we don't know them all, but they must be either 5 tuple regular or things called extremal Smith graphs. And they are strongly regular because these conditions get stronger as you go up. They're strongly regular, and all the parameters are known in terms of just one number. And we have a couple of examples, the Schläfli graph and the McLaughlin graph, but we don't know whether there are any more, but they're very restricted. But what about 3 tuple regular? It falls somewhere in the middle. Strongly regular graphs are a very prolific family, but 4 and 5 tuple regular are much, much, much more restricted. So on which side of the fence do 3 tuple regular graphs sit? And that's really my question, my two questions. So first of all, here's a little result. If k is not 3, then a graph which is co-spectral with a k-tuple regular graph is, that should say, k-tuple regular. Why? Well, let's have a look. There's a well-known characterization of regular graphs by the spectrum. The sum of squares of the eigenvalues should be equal to n times the largest eigenvalue. 2 tuple regular is strongly regular, which of course just means there are only 2 non-principal eigenvalues. And 5 tuple regular or more, you have this, well, you know all the graphs, so it's actually very easy. No 2 of these are co-spectral. And 4 tuple regular extremal Smith graphs are just defined by their parameters, and so they must be 4 tuple regular. So this proposition does not hold for k equals 3. If you take a non-singular quadratic form on a vector space of even dimension, join v and w of q, v minus w equals 0, you get a 3 tuple regular graph. It has the same parameters as certain Latin square type graphs derived from the appropriate number of mutually orthogonal Latin squares. And there are many, many, many of those, because you have to pick, you have mutually orthogonal Latin squares of order, let's say q, which is 2 to the n. You need to pick about half q of them. And of course, there are many, many ways of doing that. And most of these will give you very different and probably quite irregular graphs. So there are quite a lot of graphs co-spectral with 3 tuple regular graphs constructed like that. But the question is, are these quadratic form graphs, the only three-tuple regular graphs which have co-spectral mates which are not three-tuple regular, because the parameters must look a bit like that. If they don't, then the graph is a Smith graph, and that the three-tuple regularity follows from the parameters in that case. So this is really a question about Latin square and negative Latin square type graphs. So that's my first open question. And the second open question is, every finite group is the automorphism group of a graph. This was Frucht's theorem, and indeed of a regular graph, indeed even a cubic graph, and a strongly regular graph. So you can put, for k less than or equal to 2, you can take the class of k-tuple regular graphs, and they represent all finite groups as automorphism groups. For k greater than or equal to 5, that's false, because we only have that very limited collection of graphs, and their automorphism groups are far from covering all possible groups. K equals 4 is really mysterious. We don't know, but what about k equals 3? Is every finite group the automorphism group of a three-tuple regular graph? In other words, if you're solving a question like this, can you build enough three-tuple regular graphs to represent all finite groups or not? I don't know, but those are the questions. So that's all I have, but does anyone want to ask anything or make any comments about those?